P?
Yeah.
What you do is you take powers of your matrix or your transformation until, well, first of all, you'll sort of know, you'll know what the sizes are that if it's a small enough problem, you'll know what sizes you're looking for anyway, because you'll know how many blocks you have, right? So maybe your whole matrix is 6 by 6, and you know that you've got to have 2 Jordan blocks. So then you either have a 5 by 5 and a 1 by 1, or you have a 4 by 4 and a 2 by 2, or you have 2 3 by 3s, right? So what you can do to figure out what is the right size of the Jordan block is to start calculating powers of this transformation, right? And what should happen is, for example, certain powers of this transformation might become 0. If that happens, then you know you're not going to get cycles that are longer than that. They have to be smaller than that. So with a specific problem, it can be a little difficult to tell for sure like what cycle lengths that you want. It's usually going to come more quickly from just knowing how many blocks you need to have and knowing what your lambdas are. They may not all be the same lambda, right? So that's a good way to do that. Let me do an example of that in a minute. I'll show you kind of how you can solve that. The sort of thing. These can be very difficult. If it's a large size problem, it may be very hard to pin down how big are the blocks and how many of them are there. That can be a little tricky. But for the sizes that you guys are going to be expected to be able to deal with, it'll pretty quickly resolve itself into a specific case. Okay, so let me come back to that in just a second. I just want to put one more thing up over here, which is, this is not number 2, this is the second, well, it is number 2, I guess. It's the second application of this material, which would be systems of differential equations. Systems of differential equations. Does everybody know how to do this? This is, if you've been doing the practice quizzes, one of the practice quizzes had one of these on there, but I didn't ask it on the quiz, but I do want you to know it. Basically, any system of differential equations can be written like that. Okay? The idea is to replace it with an easier system. The easier system that you replace it with is this one. So you replace the x's with y's, and you replace the capital A with d. What is d coming from? It's coming from the diagonalization process. So q inverse aq equals d. If you're solving a system of differential equations and your coefficient matrix is a diagonal matrix, then it's very easy to solve for the y vector. Of course, that y vector that you see over there is not a vector of numbers, is it? It's a vector of functions. Right? You're solving a system of differential equations for a large number of unknown functions. So the idea is you don't like to solve this one directly, so solve this one. This one's easy, because all it is, if this is just a bunch of scalars times y, then each one of your unknown functions, yi, that's in this vector, has a derivative that's equal to lambda I times yi. And this is a differential equation that everybody should know how to solve. The solution to this is just yi of t equals e to the lambda I t. Right? So it's just exponential solutions. Look familiar? Okay, so this becomes very easy to solve. Then the question is, all right, but that's solving the wrong problem. How do you go back and solve for the x's? Well, that's where you need the other equation, which is that x is equal to q times y. So we derived that in class. If you go back to your notes, when I went over that, we derived that. So the idea is, okay, very simple here, guys. Solve this system first. This is easier. Get y, the unknown vector y. Then take y and come stick it over here next to q, and then you'll get x. Okay? Q is a matrix. It's going to be a matrix of numbers. and you're multiplying it by this vector of functions. Okay, and that's giving you this vector of functions for x, which is what you're trying to solve for. Does that make sense? Everybody okay with that? You know, the one thing I didn't do, I don't know if you'd like it if I did this or not. In other words, what if your matrix is not diagonalizable? What if capital A is not diagonalizable? So you can't find a D. Well, you can still find J, right? You can still do that, and we would just change the D to a J here. This equation is still the same. It's still true. The only thing is now you've got some ones maybe on the superdiagonal of this matrix here. So then your equations down here, they don't all become just yi prime equals lambda times yi. They might have a second term added to them, and then they become actually first order linear, which means you have to know how to solve them from 250D by using integrating factors and all that stuff. Anybody remember that? I actually think I might do an example of that in class tomorrow, just to sort of show everybody that the Jordan canonical forms is useful for systems of differential equations when you can't diagonalize the coefficient matrix. So I just wanted to see if that seems reasonable that you would have that extension there. Yeah, so it's actually pretty cool, because that you don't do in 250B. That's a system of differential equations. In 250B you don't do that. So, okay. Any questions about that? Everybody's kind of tired today, I can tell. Is that one of those days? Get some sleep tonight. We've got a busy week ahead. Let's see if we can wake ourselves up. Let's do some problems. Okay. Let's jump into some examples. I've got quite a few problems here. So let's do some practice. Okay. So let's start with. Let's start with this first one here. A is similar to B if and only if, so I want us to, this is a prove that A is similar to B if and only if the Jordan canonical form of A is the same as the Jordan canonical form of B. Actually, hold on a second. Maybe that's the one I stated last time and didn't prove it. Find my notes here real quick. Yeah, this is actually theorem 7.11. It's actually theorem 7.11. So let's see if we can write this one up. Okay. Let's start with the backwards direction. Does everybody know what similar means? Right, there's a matrix Q such that Q inverse times A times Q is equal to B, right? So that's what we would like to show. Now what we're starting with is that A and B have the same Jordan canonical form. Let's call that common Jordan canonical form J. So if the Jordan canonical form of capital A is equal to J, then what equation could we write down here? Go ahead. Equals what? Go ahead. A times Q, right? Jordan canonical form. Right? Basically, this right here. Q inverse AQ equals J. So this is J is the notation. Okay, so maybe I should say here, let J equal the JCF of A equal the JCF of B. Okay, assume that these are equal. I'm doing the backwards direction, so I'm assuming that they're both equal to the same thing. I'm going to call it J. So basically, this is for some invertible Q. All right? So we know that. What else do we know already? Right, the Jordan canonical form of B is also J, so what would the equation for B look like? Is it the same Q?
Oh, no, BP.
P inverse BP is also equal to J, or some invertible P, right? That's really what the assumptions tell us, right? The assumptions are telling us the Jordan canonical form of A is equal to J, and the Jordan canonical form of B is equal to J. It just means it's similar to J, right? So now we want to show that A is actually similar to B. Does anybody see how maybe I'm going to be able to do that using these equations? Okay, so they're equal to each other. So Q inverse AQ is equal to P inverse BP. Okay, and now what? Apply what? Q? On which side? The left side or the right side? I know you said both sides, but when you apply it, which are you applying? Matrix multiplication is not commutative. So when you say apply Q to both sides, for all I know, that's what you mean. I need to know, do you mean it like that, or do you mean it like this? Like this, right? Because you want these to cancel, right? Okay, so you get AQ equals QP inverse BP. All right, now what? Apply Q. Right multiplied by Q inverse. I don't want to get the Q to cancel here. So I'm going to right multiply by Q inverse. I'm going to get Q P inverse B P Q inverse. Okay. And am I done? Let's see, what does similar mean again? Similar means that A is equal to something inverse times B times something. So I've got the B right here. Here's A. Is A similar to B?
You just put the EG in parentheses.
Go ahead, Mark.
Just put them in parentheses.
Okay, so do you just mean like this?
The left side one, which on the inside of the parentheses, it has to be PQ inverse.
Right. See, isn't that just the inverse of the quantity PQ inverse? Okay. The inverse of a product is the product of the inverses in the opposite order. So that's what I'm going to use here. The inverse of this product is actually Q inverse inverse, which is Q, times P inverse, which is P inverse right here, times B times PQ inverse. Do you see that what I have here is the inverse of a matrix times B times the matrix? Okay? So A is similar to B. I'm going to just use my twiddle symbol for that. So A is similar to B. Does that seem reasonable to everybody? Reasonable proof? So A and B, they have the same Jordan canonical form. That means we can write these two equations down, both of them, right? But not necessarily with the same matrix here. Okay? Then I can rewrite, and basically once I set these equal to each other, then I'm just solving. And it's just all just matrix algebra here. So it's really simple. I'm showing you things that are on the level of what I would want you to be able to do on Wednesday. The idea is there's actually not a lot of writing or explaining. It's just doing a little bit of calculation. Okay? Make sense? This one to become this? So PQ inverse inverse, these are two matrices multiplied together, quantity inverse. When you have a quantity multiplied together and then take an inverse, you take basically each one separately in the opposite order and take the inverse. But Q inverse inverse is just Q. So you see, this expression here is really just that. The reason I rewrote it like this, it looks like I made it more complicated. I rewrote it like this to make it look like the definition of what it means for A to be similar to B. So I took this one, which was simpler, and rewrote it more complicated so that I could see that it's the inverse of this one over here. That's the reason we're doing that. Does that make some sense? Okay. All right, let's try and go forward with this proof. So the forward direction, and the way that is, we're going to assume that A is similar to B. Okay, so can somebody tell me right away based on that, what can I write down? Q inverse times A times Q, right, is equal to B, right? For some, this is just the definition of similar, right? This is just for some invertible Q. So for some invertible matrix Q, Q inverse AQ has to equal to B. So far so good? Okay, and I would like to show that A and B have the same Jordan canonical form. At least up to the arrangement of the blocks. So you can always move the blocks around. I'd like to show they have the same Jordan canonical form. Let's just say, let's just assume that J is the Jordan canonical form of A. Because it's got one. Every matrix has a Jordan canonical form. Let's just give it a name. And then we need to show that J is also the Jordan canonical form of B. So we just set up a name, we'll call it J. J is the Jordan canonical form of the first matrix. I want it to be the Jordan canonical form of the second matrix. So again, if I know that J is my Jordan canonical form of A, then doesn't that just mean that, you know, there is some invertible, let's say P this time, we'll use a different notation. P inverse times A times P, which would have to equal J. Does that make sense? So as long as there's an invertible, so how do I recognize that something is the Jordan canonical form of a matrix? Well, it has to be in the right Jordan canonical form, which I'm assuming J is, which means it has blocks, Jordan blocks, going down the diagonal. And our matrix, capital A, has to be similar to that matrix. So what we're saying right here is that there is an invertible matrix P such that P inverse times A times P is in Jordan canonical form with these blocks going down the diagonal. I don't know what P is specifically here. We're doing this very abstractly. But there exists a P such that that is true. So A is similar to this JCF form, which I'm calling capital J. I would like to show that B is also similar to it. Do you see how to do it? Richard, go ahead. Solve this for A? Okay. So A is equal to PJP inverse. Into here. Okay, let's just do that. So we get Q inverse. I'm going to plug in what A is, which is PJP inverse. Q equals B. So we now know that, right? Do what now? Well, this is what I need to show. I need to show that the Jordan canonical form of B is equal to J. So doesn't that mean that just as when I knew that the Jordan canonical form of A was equal to J, we had J by itself here equal to something? So can I get J by itself here? Yeah, I can. And when I do that, what's going to happen? Let's see. B's going to be here. I'm going to left multiply both sides by Q. Then I'm going to left multiply both sides by P inverse. Then I'm going to right multiply both sides by Q inverse, and then right multiply both sides by P. So Basically, you're clearing out the left side and just leaving the J there and moving everything else to the other side. And the point is that this, again, see, the proof is actually very similar to the other direction. This is just Q inverse P inverse times B times Q inverse P. So it's something inverse times B times something equals J. So that proves that the Jordan canonical form of B is equal to J. Everybody okay with that? Because, again, how do I recognize the Jordan canonical form of a matrix? It has to be similar to my matrix, and it has to have Jordan blocks. It has to have the form of the Jordan canonical form. Well, this equation shows me that B is similar to J, and I know that J has the proper structure because I assumed it was already in a Jordan canonical form for another matrix. Clear enough? Okay, so that's a nice, so this is theorem 7.11, and you will want to know this. I should have put it in the overall recap. But this is a very, very nice problem. Let me show you kind of why you might want to know that fact. We're going to do another problem. And this will show you why that fact is so helpful. Why that theorem is so helpful. Number 2, are these similar? Okay, so here we go. The first one is capital A is the matrix 7, 1, 0, negative 1, 5, 0, 1, 0, 6. And B is the matrix 6, negative 1, 1, 0, 6, 0, 0, 0, 6. Now, guys, we know that similar matrices have lots of things in common. They have to have lots of things in common. So if they don't, if there's something that these two matrices don't have in common, then we will be able to say that they are not similar. For example, if these two matrices don't have the same determinant, then they're not similar. If they don't have the same lambdas, then they're not similar, right? So in some sense, if the answer is no, they're not similar, it would be easier for us to decide that. But what I don't want you to make the mistake of doing, and a couple people did this on the quiz, is to say something like, well, they have the same determinant and they have the same eigenvalues, so they must be similar. We know that's not true, right? You can have two matrices with the same lambdas and the same determinant, and they are still not similar. So how, if I was going to try to say yes to a question like this, if the two matrices were similar, what would be the way that I would maybe try to make a positive conclusion? I'm just curious. So a negative conclusion is easy. Just find something that doesn't agree. Wrong determinants or wrong eigenvalues, whatever. How am I going to say yes to a question like that? Exactly. The first problem. Look at their Jordan canonical forms. And ironically, finding the Jordan canonical forms means I have to find the lambdas. So if we find the lambdas along the way and they're not the same, we'll be able to say no. But if we find their Jordan canonical forms and they are the same, then we'll be able to say yes. So that's how you want to approach this problem. Basically, you want to find the JCF of this and the JCF of this and see if they're the same. So I'm going to do this fairly quickly, the kind of the tedious technical part. We need to do the determinant of A minus Ti, right? And that's just going to be the determinant of, this is the determinant of the matrix 7 minus T, 7 minus T, 1, 0, negative 1, 5 minus T, 0, and 1, 0, and 6 minus T. And to evaluate that, how should I evaluate this determinant? The third column, exactly. So we'll get 6 minus t, and then there's a 2 by 2 submatrix here, which is 7 minus t times 5 minus t, and then plus 1. So that becomes 6 minus t times t squared minus 12t plus 36. So would you guys mind if I just tell you right away that your solutions are going to be 6 and 6 and 6? 3 6s there. Okay? If I look at this matrix, can you tell me the eigenvalues right away? Right, it's upper triangular, so they have to be just remember, for upper or lower triangular matrix, the eigenvalues are just on the diagonal. That's important because I might ask you on Wednesday to give me examples of things. And if I ask you to give me examples of something and it involves eigenvalues, well, you'd like to make matrices whose eigenvalues are easy to spot on the fly, then upper triangular matrix will do it. Okay, so they have the same eigenvalues. Does that mean that the matrices are similar? No. So we need to find the Jordan canonical forms. That's really how you're going to get a positive answer, right? Is to see if they have the same JCF. So let's think about Jordan canonical. We're practicing Jordan canonical forms here. We've erased it now, but we had some notes up earlier about sizes of blocks and number of blocks and all that stuff. Let's look at the Eigen Spaces. Okay? Remember that the number of Jordan blocks is just the dimension of E sub lambda. So let's do it for each matrix, okay? So for capital A, we're going to look at the null space of A minus 6I, which means the null space, I'm using capital N for the null space. I'm going to subtract 6 from the main diagonal. And you guys should check me that I did it right. I'm going to get that matrix. If I think about these columns as corresponding to variables, notice that the last line tells me that x is 0. And then the first line tells me that, of course this line is the same, x plus y is 0. So x plus y is 0 and x is 0, so therefore x and y are both 0. But z is free, right? So I'm going to get one eigenvector, is 1, 1, 1. I'm sorry, the eigenvector is 0, 0, 1. Right, 0, 0, 1. And of course that corresponds to lambda equals 6. So how many Jordan blocks does the matrix capital A have? Just one, right? So I actually already know what the Jordan canonical form of A is. The Jordan canonical form of A, if there's only one block, has to be one giant 3 by 3 block, right? It's actually going to look like that. One block of size 3. Make sense? One block of size 3. The number of blocks is just the number of linearly independent eigenvectors. So the dimension of E sub lambda in this case is only 1. This eigenvalue pretty badly fails to pull its weight. Right? Does not pull its weight here. With me? Okay, what about the other matrix, B? Well, for B, I can do the null space of B minus 6I. So that's the null space of, I subtract 6 again. And that's what I'm going to get. You all right with that? How many free variables do I have? 2. So how many eigenvectors am I going to get? 2, right? So I'll get, and the free variables are just, well, the third variable is free. And so if z is equal to t, then notice that y also has to be t. This first row says that y equals z, basically. So I'm going to say 0, 1, 1. Yeah, maybe?
For this question, do we have stopped there?
We actually already, we could stop already because we already know that the Jordan canonical form is not going to be the same.